I want to talk today about water-rich planets. And if you go away from Earth-like planets and have much more water on top of the silicate mantle and the iron core of a planet, how this influences potentially the habitability of these planets. And this study is actually quite an international study. So it's with contributions from Belgium, from Germany, from Austria and from France. Sadly, none of my other co-authors are part of this cost action yet, but I will try to get someone into the team before publishing the paper finally, so it will be a cost paper. But first, as a motivation, we've heard in a lot of talks before that there have been several exoplanets detected so far, even exoplanets in the habitable zone. But if you actually look at the data sets, I'm not sure how well you can see it, but here are a lot of different points where we have mass and radius measurements or estimations available. And you can see that pretty much the points are almost everywhere in this picture for the mass of the planets and the radius of the planets. Here the maximum mass is 10 Earth masses, so we are just looking at sub-Neptune planets or super-Earth planets. We can actually erase for a second just these planets that are in these regions that are very heavy, for example, very dense planets, or the planets where we have a very large contribution of an external atmosphere. And just have a look at these planets here. You can see two main regions that I plotted here, the two shaded regions. The blue one, these are planets that where you typically need to explain, need a lot amount of water to actually explain the radius that you observe and the mass. Whereas down here you have a lot of planets that could be similar to Earth. They could also have a large amount of water. We don't know it because we only know the mass and the radius of these planets. But actually in my talk I'm going to focus more on this blue region, so the planets where we have a large amount of water. So in this green circle, for example. So actually the search for water worlds, or the first papers on the possible existence of water worlds, started more than 1 decade ago. Here's a paper by Kuchner from 2003 actually, where he says that due to the migration of planets, it should be possible that there are exoplanets, except Neptune or Neptune-like planets that form outside of the snowline and then due to migration move inwards, having a slowly evaporating steam atmosphere. And in principle, they should be rich in water, and we would have these water worlds available. These papers were followed by other papers looking, for example, at possible interior structures and compositions of these ocean planets or water worlds. Here's just for comparison, it's plotted the interior structure of Earth, where we have an iron core and on top a silicate mantle, or a super-Earth with a larger iron core, the larger silicate mantle, or the same case, actually the same mass, but with a substantial amount of water. And due to the substantial amount of water, and because water has a smaller density than rock, and rock has a smaller density than iron, actually the radius of the planet is much larger than for the super-Earth planet, where you have no water at all. Then in 2006, the first planets were detected that were characterized as possibly being sub-Neptune planets. So here you can see 2 planets that have been discovered outside of the habitable zone in the mass range of approximately Uranus and Neptune. So people started to actually speculate more and more about the possible habitability of these planets. And if you want to learn more about these planets, about the evolution of water-rich planets, what you can do is to first look at the interior structure of these planets. So the approach that I use is to take different amounts of water, different amounts of rocks, different amounts of iron, mix it up, stir it together, and see what kind of planets I can actually get out of it. So in these cases, I always assume that the planets are differentiated. So you have, again, this iron core, the silicate mantle, and this water shell. If I say water, I actually don't necessarily mean liquid water. It can also be ice. So this has been done by several other authors in the past decade as well. Here, for example, is a paper from Zatang et al. From 2007, where you can see again a mass and radius diagram, and you can see two trend lines, one line where you plotted all the terrestrial bodies in our solar system, and another line where you actually plotted all the icy bodies in our solar system, or several icy bodies of the solar system, ending with Uranus and Neptune, which are a little bit above this line for Titan, Ganymede, and Callisto. So the thing is now, if we discover a planet of a specific mass and a specific radius, we don't know what are actually the components that we put into the pot, and then we stir it and then we get the interior structure. It's the other way around. We have to think what are possible interior structures, what are possible compositions of the planets that can explain a planet with one mass and one Earth radius, excluding that there might also be an atmosphere. So here, for example, you can see different kind of models with variable water amounts from 0 to about 25 weight% of water. And the radius of a planet starting from 0, from the core, from the center of the planet to the surface. And here you can see different possible interior structures for one Earth mass, one Earth radius. This is fixed. So you can see that depending on the ratio of iron and silicates, you can actually have substantial amounts of water and still have a planet which would look like a second Earth. Of course, the cases here on the right side are less likely. But you would not be able to distinguish between a water-rich planet and a terrestrial planet. On the other hand, if you assume now that we discover a planet with one Earth radius, but only half the mass of Earth, so a less dense body than Earth, then actually, apart from the possible influence of an atmosphere, there is no possible way to explain the radius and the mass of the planet without the amount of, or substantial amounts of water. So in this case, something like 50 weight% of water. So there are actually some planets where we can definitely say that they have to have a large amount of water. But the problem is, even if we can say there is a large amount of water, we don't know exactly how much it is. So if we want to make some statistical analysis about the possible habitability of these planets, we always have to see that, like, what are the ranges of amounts of water where we can still speak about habitability, and where are the limits for the models. So even though I showed before that in principle, you can have a very large amount of variations for the water content of the planets to explain a specific mass and radius. With some statistical analysis, as has been done by Grasset et al. In 2009, you can make some probability measurements and find some more likely models for water. But still, it's not possible to directly define or determine the composition of a planet, of an exoplanet. What you can do next, if you actually wonder about the possible habitability of these water-rich planets, is to look at the maximal depths of a liquid ocean water before it would actually form high-pressure ice. So this is a study, for example, done by Jan Alibert, who's the chair of this session, but also by Zotang et al. In 2007, for example, looking at, depending on the amount of water and depending on the mass of the planet, here it's again in Earth masses, how deep can a water layer be before you actually form high-pressure ice? And just to tell you, I'm not sure if you can see the numbers, but for an Earth mass planet, something like 2-3 weight% of water are already the limit for a liquid ocean. This study you can also extend to look, for example, at different surface temperatures. So not surface temperatures like on Earth, but actually look at higher surface temperatures, because if you assume that there is some kind of an atmosphere, there might be greenhouse effects and we would have a heating at the surface. But even if you go to higher surface temperatures, from Earth-like surface temperatures to, for example, 100 Kelvin higher surface temperatures, we are still limited to few weight% of water. So what is it now about the habitability? So we have these rather shallow liquid oceans, and then we form this high pressure ice layer. The problem is now for habitability. Actually, what we want to have is that the life, if it could form potentially in the liquid water would need have access to nutrients, to building blocks of life. So we need an interface between liquid water and the silicate mantle. So the question is if it's somewhere possible that instead of transporting material or building blocks of life from the lower part of this water layer to the liquid part, if you can actually have melting of the high pressure ice layer at the bottom of this layer. So here's just for an example how on the one hand the melting temperature of ice or of water looks like and the typical temperature profile in the interior of such an ice layer. So here you can see first this is the liquid part and here's the high pressure ice phases. The black line corresponds to the melting temperature. So you have in this liquid part you have a temperature profile that increases with steps, and at some point it crosses the line of the melting temperature of ice and high pressure ice forms, which is exactly here. And then typically it is assumed that this temperature profile increases adiabatically with depth. Now, if you actually look now at the silicate mantle, so at the bottom of this high pressure ice layer, there we actually assume typically that we have radioactive heat sources, maybe even tidal heat sources. And what happens then is that you have increasing temperatures in the silicate part, in the silicate crust for example, and if you have ice, then the heat cannot be transported out of the crust very efficiently. So what actually happens then is that the temperature is increasing, and at some point it can actually happen that you melt the high pressure ice layer from the bottom, which would then actually lead to a possibly habitable region, because then you have liquid water and you have the interaction with the silicate part. So to actually model this, we use an interior structure model that has been developed in the past years for terrestrial planets and water-rich planets, where we account for the possibility to have a water high-pressure ice layer and possibly melting of the high-pressure ice layer at the bottom. And the temperature profile from the surface to the interior is calculated completely self-consistently over time. So here's now 3 examples of simulations that we have done for a planet of 1 Earth mass, 1 Earth radius, and it's different amounts of water in weight percent that we add on top of the planet. So just here, for example, if you have 1.58 weight percent of water for an Earth-like surface temperature, we do have an entirely liquid water layer. If we now go to just slightly higher values of water, what happens is that we have a high pressure ice layer. It's just in the bottom 10 kilometers in this case. But we can also have melting at the bottom of the high pressure ice layer for a few kilometers. In this case then we have a more efficient heat transport through the ice layer because we have this liquid ocean down here, which means to rapid cooling, a phase where we have only high pressure ice layer and then it's melting again. And then at some point we get a stable configuration where we have water, ice, water. If we go to larger amounts of water, so in this case it's still not very much, but this is just an example simulation. In this case 2.6 weight percent of water. What actually happens is that what we have here, so this increasing amount of liquid water, rapid cooling, completely frozen lower part of the ice, this is something that happens actually episodically. So you never have a stable configuration where you have liquid water at the bottom of the ice layer for long time scales. Still, it's questionable if this is not maybe possibly still habitable, because life can in principle survive in ice phases as well, if it becomes liquid again later on. So this is why we defined now 3 different habitability classes if you're looking at water-rich planets, going from entirely liquid water layers to this water, ice, water phase, and the less likely habitable case where we have high pressure ice which cannot be molten at the bottom anymore from the heat coming out of the interior. And there are additional influences like plate tectonics, volcanism, where I come back to later at the end of my talk. So now we can do some kind of quantitative analysis to see when we actually have this lower ocean and if it's an episodic or a stable lower ocean. So here's now a reference simulation. It's an Earth-like configuration, an Earth-like planet with different amounts of water. So here on the left side you can see the amount of water from 0 to 15 weight%. And here the planet mass goes from 1 to 10 Earth masses. What you can see is 3 different regions. So this region first is a green region. It's a case where you have an only liquid ocean, similar to the studies that have been published before on the maximum depths of a liquid ocean layer. Then we have here 3 regions going from yellow over orange to dark orange, where we have this lower ocean layer, which is either stable or episodic. And we have this region down here. The numbers give the depth in kilometer, where we only have an ocean ice layer, and the ice layer cannot be molten again from underneath. So this would be the non-habitable cases, habitable, and possibly habitable. Now let's concentrate on the case of just one Earth mass and actually look at different influences. So first, here's the case, so exactly what I've shown you before, but now actually stretched over different water layer thicknesses in kilometer, so going up to 1,000 kilometer, and the episodicity of the lower ocean. So 100 means you have a stable lower ocean, 0 means you have only ocean high pressure ice and no melting from underneath. And you can see that if you increase the water layer thickness for a surface temperature of 290 Kelvin, that at some point, very soon after you form high pressure ice, you will only end up with this episodic cases. So in like 60–70% over the time, averaged over the time, you will have liquid water at the bottom of the high pressure ice layer, but in between it's freezing out. And this drops then to the not habitable cases. How does it change now if we look at higher surface temperatures? So here's the same simulation, but just for higher surface temperatures of 370 Kelvin. And you can see first that, of course, the green region extends now to much deeper oceans, but also the stable lower ocean region extends now to almost 1,000 kilometers. So where if you only look at the green cases, habitability would be limited to 400 kilometers. This lower ocean habitability extends to almost 1,000 kilometers. So here just again to show the 3 different regions that we have. So now we can look at more quantitatively at it and see what are the actual influences of different parameters on our study results. So the surface temperature I've just shown you as one example. But what happens, for example, if you have different initial mantle temperatures, if you have different heat sources, like radioactive or tidal heat sources in the mantle? What if you have a more efficient crust enrichment in radioactive elements? What kind of convective regime we have if you have a stagnant lid layer or plate tectonics layer on top of the silicate mantle? Or, for example, how does the iron content change in relation to the Earth value? And this actually led to more than 15,000 simulations. I'm not showing you all the simulations results now. I will just show you one slide for the case of one Earth mass, where we just show for the variation of the different factors plotted over the water layer thickness. It's always going from 0 kilometer to 1,800 kilometer. How the different regimes that I showed you before depend on the parameters. And what you can see is, for example, that if you have plate tectonics, so 1 means plate tectonics, 0 is stagnant lid, this habitable or episodic habitable regime extends to much, much deeper layers. Heat sources also have a slight effect, as well as a mantle temperature or initial mantle temperature. The surface temperature has the strongest effect actually on this stable or lower ocean layer. And there are other effects that have a less interesting influence of the results. What we did then was to add 5,140 Monte Carlo simulations to actually look at, if you now use combinations of all these different parameters, can we make some statistical approach, some statistical analysis of the possible habitability of water-rich planets. And now what you can see here now is all these 5,140 simulations summarized in one picture over the planet mass and the amount of water. The picture is cut here at 10 weight percent, but the cases actually extend to higher weight percent of water. And the color coding is again as was used before, with green meaning that we have a liquid ocean layer. Red means that we have this ocean ice configuration that is not molten from underneath and probably not habitable. And in between, a lot of cases in the yellow-orange color coding, yellow meaning that you have a stable lower ocean, orange meaning that you have an episodic lower ocean. And what you can see is that in general, this green region extends now to almost twice the depth compared to the results before, if you take into account this habitable lower ocean. And the most important factors, also from the quantitative study before, that have an influence on the results of this habitability are the surface temperature, the amount of radioactive heat sources, and also tidal heating, of course, and the ice rheology, which still has to be determined in laboratory studies. So we can also summarize the results in the table. Here you can see again the different regimes, the liquid ocean, the mixed lower ocean case, and the not habitable case. On the one hand, one can compare plate tectonics and stagnant lit simulations with each other. And what we see is that these episodic cases appear more often for plate tectonics than for stagnant lit regimes, but otherwise we cannot see a strong influence of plate tectonics on the existence of the lower ocean. But if you just look at the maximum depth of the liquid ocean layer that was observed for 1 Earth mass or for 10 Earth mass, you can see first the results in kilometers and then in weight percent. If you just look at the classical case of the liquid water ocean at maximum 1,250 kilometer or 20 weight percent of water, high pressure ice forms, and one would argue that these cases are not habitable anymore. But if you take this possible, maybe episodic lower ocean into account, you can go to about 50% deeper water layers. For 10 Earth mass planets, this is even a factor of 2, the change in possible habitable water layers. Just shortly saying something about melting and plate tectonics. So we were investigating also if, depending on the depth of the water ocean layer, if we actually can still have melting or volcanic activity at the bottom of this ice layer. Why? Because if you think about the origin of life or possible origin of life on Earth, it has been argued that you need hydrothermal vents to actually have this chemical energy available to form life. So if we now actually look at these water-rich planets, the only possibly habitable region would be at the bottom of the ice layer, which is molten. But if you don't have any volcanic activity and a very thick stagnant lit underneath, it's not that likely that we actually would have active hydrothermal activity. So we were looking at, depending on if we actually have plate tectonics or stagnant lit, if we can have melting. And here just is plotted 2 different temperature profiles in the silicate mantle. So starting here now really at the bottom of the ice layer or at the top of the silicate layer. If you have the stagnant lit case, like on Mars, for example, the temperature slowly increases with depth until you're in the convecting part of the mantle. Plate tectonics, on the other hand, leads to the mantle material reaching to almost to the top of the silicate part, and therefore if the black line is here the solidus or the melting temperature, And just in this specific comparison, you can see that for plate tectonics cases, you would get melting, whereas for stagnant lit, you would not get melting. So we're looking now at different simulations. First, there's one other thing that I want to shortly address, which is that if you actually compare the density of solid material in the mantle and liquid melt, molten material in the mantle increases, or the depth of the molten material increases most deeply with pressure, with depth, which means that there's only a limited region of pressures possible where melt would actually rise upwards. So at some point, if you have very high pressures induced from the overlaying water ocean, even if you would have melting in the mantle, it would not rise upwards and you would not have volcanic activity. Which leads that if you have melting, it typically rises directly directly underneath the stagnant lit, and then you can have, due to convection, bring more primordial material to the surface and have more advanced melting. And here's a comparison of how much crust you can develop in kilometers, maximum 45 kilometers in this case, for either stagnant lit cases or plate tectonic cases, depending on the mass of the planet and the water layer thickness. And just as a short summary, saying that if you have plate tectonics, then the regions where we have can have melting at the bottom of this ice layer is extended to much, much deeper water layers and higher masses. So it's good for the habitability of the lower ocean region. And this is slightly depending on different factors, like, for example, the number of heat sources and initial parameters. So in summary, planets with large water amounts likely form high-pressure ice at specific depths, but this doesn't necessarily rule out the habitability of these planets, because depending on the interior, this high-pressure ice layer may melt from underneath and actually lead to a quite nice habitable niche at the bottom of the high-pressure ice layer. And very thick ice layers will not be able to melt again from underneath. And the maximal habitable water, or the maximal depth where water layers can still be habitable, is approximately twice as deep as if you just look at the maximum depth of an upper ocean layer. So with this, I would like to thank you.